Hello everybody, and welcome back to the final lesson of Algebra 2. We made it, everybody. We did it. Today, we are going to finally find the applications of trigonometric functions through modeling them. So, let's do it. Trig functions always repeat. A sine wave will repeat over and over and over and over again in the same way. So will cosine wave, and heck, even a tangent, cotangent, secant, cosecant, all of that will repeat. Because of that, it's really useful for anything that repeats. Think like a pendulum on a grandfather clock. Because it goes back and forth over and over and over again, you can model it using a sine or a cosine function. Similarly, sound waves. Sound waves can repeat, and if they do, you got a sine or a cosine. Seasons of the year repeat. You can represent the temperatures throughout a year using sine and cosine. Waves will go up and down, so you can use those with a sine and cosine wave. We call this anything that repeats over and over and over again. We say that they have a frequency to them. The frequency is something very specific. The frequency is the reciprocal of the period. So when we say the period, let's say our period is 2 pi over the absolute value of b. That's what we learned last section. The frequency of something is going to be the absolute value of b over 2 pi. It's just flipped. The frequency gives you the number of cycles in a given time. So, for instance, if I wanted to find the waves throughout a day, I could say that the frequency would be divided by 2 pi, but our b value would help us determine how many times per day we have high tide or low tide. Let's take a look at an example of frequency and see how we can apply it to find an equation. So, a sound consisting of a single frequency is called a pure tone. The most famous pure tone, by the way, is 440 hertz. That's an A note. An audiometer produces pure tones to test out a person's auditory functions. An audiometer produces a pure tone with a frequency of 2000 hertz, which is a unit of cycles per second. The maximum pressure P produced from a sine tone is 2 millipascals. And we want to write and graph a sine model that gives the pressure P as a function of time in seconds. So right away, we've got a very important piece of information. P can be modeled using sine. So we can model it using A times the sine of, well, we're not using x here, we're using t for time, so it'll be A times the sine of b times t. Cool. We also know quite a bit of very important information. Is there a way we could find out our A value from here? Well, the maximum pressure is 2 millipascals, and we're starting at 0 pressure, so it makes sense that our amplitude is 2. 2 millipascals is our amplitude. Since our amplitude equals 2, our A value equals 2. And since we weren't given any indication that this would be an upside down sine wave, we wouldn't need to write -2. We could just say that it's at 2. Cool, we're already on a good start. We have one of our missing variables. But we also need to have a period, and this is the problem. We're not given any indication of a period. We're just told that the frequency is 2000 hertz. But wait a second. If the frequency is 2000 hertz, isn't the period just the reciprocal of that? So, if the frequency is equal to 2000, then all we need to do is flip this to find the period. The period would be 1 over 2,000. That's the reciprocal. Cool, so we've actually got a good indication of the period. Here's the problem. Our period is 1 over 2,000, but that doesn't give us a b value. What we do know is that the period can be represented as 2 pi over b. How do we solve for b? Well, we would have to actually cross-multiply to solve this. So 1b equals 2,000 times 2 pi, that's 4,000 pi. We have an equation, everybody. The equation is p equals our amplitude of 2 times the sine of 4,000 pi times t. Done. All we need to do now is graph this. So let's figure this out. Last class, we did a lot of stuff with our graph based on, the actual graph itself. Today I want to try something a bit different. I want to see if we can make our graph based on just our key points. So first off, did we shift up or down? No, we didn't have an H or a K, so we're fine. Let's start by remembering the key points of a sine function. Our sine function is going to basically, here's a little sketch of it, start at 0, go up to a maximum, go back down to 0, go to a minimum, and then go back to 0. This is our normal sine. So, we can actually figure out that we're going to start with a key point as an x-intercept at 0. So 0, comma, this is the sine wave when we move up or down, it's going to be 0, comma 0. How often do the x-intercepts repeat? Last section, we mentioned that it repeats every half a period. Well, if our period is 1 over 2,000, that means that it's going to be half of 1 over 2,000. So we're going to repeat this every half 1 over 2,000. Which means we'll get 1 over 4,000, comma 0, and 1 over 2,000, comma 0. That's the full period when it ends. So we've got our x-intercepts. Let's see if we can find our maximum. There's two ways to do it. The maximum you can think of as going to be halfway in between the 0 and 1 over 4,000. Or you can just take it as a quarter of the period. Either way, the maximum happens at 1 over 8,000. And what's the highest our graph is going to go? Well, it goes up to our amplitude. Our amplitude is 2, so it's going to go up to 2 millipascals. Lastly, our minimum is going to be halfway between 4,000, 1 over 4,000 and 1 over 2,000. We might be able to predict what that's going to be. But another way to think of it is, it's going to be our fourth point here, meaning it'll be 3/4 of 1 over 2,000. 3/4 of 1 over 2,000 is 3 over 8,000. We go from 0 to 1 over 8,000, 2 over 8,000, which is 1 over 4,000, to 3 over 8,000, it's going to be at -2, because that's the lowest part of our amplitude, to 1 over 2,000, or 4 over 8,000. We've got our 5. So graphing this from here becomes a walk in the park. With this method, we have found our key values first. We know that our period is going to be 1 over 2,000, so that's going to be our final point. Cut it in half to get 1 over 4,000. Cut it in half to get 1 over 8,000. Go between 1 and 4,000, 1 over 2,000, to get 3 over 8,000. And we can just plot all of our points that we just found. Bam, up, bam, down, bam. And yes, the bams are required. This is our model, of this particular sine wave. We could say that this frequency wave can be modeled using this sine wave. I do get pretty tired of saying sine wave, so I think it's about time we give a formal name for what a sine wave can be called. The graphs of sine and cosine functions, I don't know why I just said there, are called sinusoids. Sinusoids. Think of it like how a quadratic graph is called a parabola. The sinusoid is the shape of the graph, whereas we can actually call this a sine or a cosine function. One way to write a sine or cosine function that models a sinusoid is to find the values of a, b, h, and k. Remember, absolute value of a is the amplitude, 2 pi over b is the period, h is the horizontal shift, k is the vertical shift. Let's do it. Here, for example 2, we have a sinusoid, as you can see from the shape. We're trying to find what function will model it. Well, we've got some interesting questions to ask. First of all, should this be a sine wave, or should it be a cosine wave? To figure that out, let's see what the starting point is. At 0, our y-intercept is here, at 2. Then it goes up to 5, then back to 2, then down to -1, then back to 2, then up, then middle. So what type of graph starts in the middle and goes up? That's going to be a sine wave. Okay, cool. So this sinusoid can be modeled using the following equation. Y equals A times sine of B times x minus h plus k. We just got to find those 4 missing variables. Let's start with A, the amplitude. To find our A value, we have to figure out how far up or down from the middle we are going. So let's actually start by finding that middle of our graph. The midline, the middle of our graph, can be found in between our maximum and our minimum. In this case, it's at 2. But do you want to know a mathematical way to solve for the midline? Since your midline is always going to be exactly halfway between your maximum and minimum, you can just do the maximum plus the minimum divided by 2. We can take the average. In this case, it's going to be 5 plus -1 divided by 2, which is 2. So our midline is y equals 2. Cool. We have found our k value because the k value is our vertical shift or our midline. So we know that k equals 2 because our midline is at 2. Neat. If we're graphing a sine wave, do we have a horizontal shift? Well, sine waves are supposed to start in the middle. So no, we didn't move left or right at all. Whew, we got lucky on that one. Our h value is 0. We don't actually have any horizontal shift. Let's focus back on the amplitude now. We went off on a bit of a tangent there to find the midline. But we go from the midline up to 5, and we go from the midline down to -1. So how far away are 5 and -1 from 2? That's 3 away. We can plus 3 to get to 5, or minus 3 to get to -1. So our A value, our amplitude, must be 3. Nice. Another different mathematical way to find the amplitude is this. Take your maximum and subtract your minimum and then divide by 2. It's not the same as the midline where you're adding them together. So to find the amplitude, we can always take the max minus the min and divide by 2. Since our maximum is 5, our minimum is -1, 5 minus -1 is 6, that's 3. So that's how we got our A value. Finally, our B value is going to be the tricky one. Our B value can be found by finding our period. We want to find after how long it takes for us to repeat. Let's look at the graph. We go up, middle, down, middle, up, middle, down, middle, up, middle, down, middle. So it seems like the first 5 points, up, down to middle, back to the down, back to the middle, represents our period. Well, how far away is this point from 0? Well, it's halfway between 0 and pi, so this missing period is pi over 2. Our period is pi over 2. But also recall that the period is 2 pi over our B value, right? How could we solve for our B value here? Well, we've got 2 fractions. We've got a pi over 2. Oops, let me rewrite this because I messed it up. We've got a pi over 2, and we've got a 2 pi over B. Let's cross multiply. So pi times b equals 4 pi. Can't we just divide both sides by pi? Our b value is 4. We've just written an equation based on this graph and nothing else. Y equals 3 times the sine of 4 times, well, x minus 0 plus 2, which means we can just have our final answer be 3 sine of 4x plus 2. Done! Next up, we have something called circular motion. If something moves in a circle, like you can imagine the jump rope going in a circle towards the viewer and away from the viewer, or going in a loop, you can model it using a sine or cosine wave. So, 2 people swing jump ropes, as shown in the diagram. We're doing double dutch, everyone. The highest point of the middle of each rope is 75 inches above the ground, and the lowest point is 3 inches above the ground. The rope makes 2 revolutions per second. Uh-oh, we've got a cycles per time thing going on. We've got to remember what that is. We want to write a model for the height h of a rope as a function of time, given that the rope is at its lowest point when t equals 0. Okay, that's a lot to take in, but let's start with what we know. We have a maximum of 75 inches. We have a minimum of 3 inches. What were the 2 things that we can find using the maximum and the minimum? Well, you remember that the 2 things we can find are our midline, or our k value. K is going to equal the average of these 2. What happens when we add them together and divide by 2? So 75 plus 3 divided by 2 is going to give us our midline. 75 plus 3 is 78, divided by 2 is 39. So our k value is 39. Let's write that down somewhere. K equals 39. Love it. What else can we find using our maximum minimum? Well, we can find our amplitude. Our amplitude was maximum minus minimum divided by 2. So the amplitude is going to be whatever 75 minus 3 divided by 2 is. That's 72 divided by 2. 72 divided by 2 is 36. Now be careful here. This means that our a value will start either at the peak or going to the peak, whether we decide it's sine or cosine. Let's first figure it out, if it's going to be sine or cosine. If it's sine, that means that we're starting in the middle at 39 feet. But we're not starting in the middle at 39 feet. We're starting at its lowest point when t equals 0. So our function is actually going to look something more like this. We've got a low point, we've got a middle. We've got a high point, we've got a middle. We've got a low point. What on earth is this? This looks like a flipped over cosine wave, because cosine usually starts the highest and ends the highest. Uh-oh, if it's flipped over, is our a value going to be positive 36? No, that wouldn't make sense. If it's flipped upside down, that means we have a negative a value. Our a value is negative 36. So that was a good catch. From here, the only thing we need to see is if we are, in fact, horizontally shifted, and we need to find our period. Thankfully, if we know that we're starting at the bottom, cosine normally starts at the top or bottom. So we didn't shift over at all. Our h value is 0. We don't need to worry about a phase shift. But how do we find our b value? We know that the rope makes 2 revolutions per second. But that's not a period. What is that? 2 revolutions per second is a frequency, cycles per second. And frequency is the reciprocal of a period. So, here's how we can find this. The frequency is going to be 2, so the period is going to be 1 over 2, the reciprocal. But a period is supposed to be 2 pi over our missing b value. So how can we solve this? Well, to find our b value, we can cross multiply. 1 times b is b, 2 times 2 pi is 4 pi, so our missing b value is 4 pi. Let's put it all together. We're writing our model for h, the height of the rope, and we know we're going to be using the formula for cosine. A times the cosine of b, x minus h, plus k. Our a value was negative 36. Our b value was 4 pi. We didn't have an h value, so we could just write 4 pi times x. And our k value was 39. So this is a model to represent the height of the jump rope. Sweet! Oh, I just realized something, everybody. I forgot to mention that instead of x, we should be using t because it asked for time. So sorry about that, but the concept is still the same. Last page. This is the last thing that we are going to do in Algebra 2. And frankly, it's kind of fitting that it's going to be a regression. We have done regressions in Unit 1, as well as in Unit 2 and Unit 3. We've done them every so often. But this time, we are doing something called a sinusoidal regression. What this means is, given some points, if we believe that these points somewhat model a sine wave or a cosine wave, we can actually use a sinusoidal regression to find what equation it will get. First of all, here's the deal. This shows the number of hours of daylight in Denver, Colorado on the 15th day of each month, where the first month is January. February, March, April, May, June, July, August, September, October, November, December. This, we might suspect, is a sinusoidal shape. It might be a sine or a cosine function. The reason is, the number of daylight hours per year goes up and then down, down towards the winter, and then up in the summer and down in the winter. Anything that's cyclical, like the seasons, will be repeating. We can use a sign to represent it. I am going to use a graphing calculator to do this sinusoidal regression. So, here are the steps. And we're going to do these steps live as we talk about them. Number 1, we want to put our data into a table. Specifically, we are going to use the Stat button table. So if we take a look at the Stat menu, we can click on Stat, Edit, and we'll get our table. So I'm going to take a second to plug all these values in. I'm going to say that list 1, or L1, is going to be our t values. I'm going to say that list 2 is going to be all of our n values, the number of hours of daylight. I'm going to skip ahead after I put all those numbers into the table. Alright everyone, here is our table. I plugged in all the values. They should match up with the graph. Before we go on to the next step, I want to show you how you can see these points on your graph. First things first is we need to turn on our stat plot. The stat plot button is right above the y equals, so we click second, y equals, click enter, and turn your stat plot on. Make sure the x list and the y list match what you're trying to graph. We can click graph, and if your zoom was in standard, you would see barely one of the points. So that kind of sucks. To view all your statistic points, go to Zoom Stat. That'll zoom out to see all the points in your stat plot. And we can see very, very prominently here that this looks like a sinusoidal function. In fact, it looks like an upside-down cosine almost, or maybe a shifted-over sine. So we're on the right track. Next up, we want to graph the scatter plot, which we just did. Again, a scatter plot is when you have a bunch of discrete points that aren't really connected by anything. If it appears sinusoidal, we can do the regression. So, we have to perform the regression. To do a sinusoidal regression, we're going to start by going to Stat again. Then we're going to click the right button to go to the Calc menu. So let's do that first. I'm going to click on Stat here. I'm going to go one to the right to go to Calc. And they kind of hid sinusoidal regression pretty far down. You're going to want to go over to option C where it says Sine Reg. So we got to go through the numbers before we get to the letters. 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, A, B, whoops, I was almost there and I clicked the wrong button. C is Sine Reg. So we click enter. Here's something interesting. For a sinusoidal regression on these calculators, it says iterations. Iterations is something that's ultimately your choice to change or not. For iterations, these just mean accuracy. And you can use any number between 1 and 16. If you use 1, it's not going to be accurate, but it's going to be very quick. It's like if you asked me what 57 plus 40 is and I said 90. It's not correct, but it was quick. If you go to 16, it's going to actually process much slower, but it'll be super ultra precise. 3 is usually fine for our purposes, but if you were doing a project or something, hint hint, you might want to set the iterations higher so you're as accurate as possible. Make sure your X list and Y list match your table. Mine doesn't. I said that list 1 was our T's and list 2 was our N values, so to change this from a certain list number to a different one, you actually have to go to the list variables, second list. And since we want L2, I'm going to click L2. it says the period, if you know the period of your graph, you can put it in here, and it will assist even more with the accuracy. We know the period is going to be 2 pi over b, but it doesn't help if we don't know our b value. So I'm going to choose to leave that blank for us here. Instead, we should go down to where it says store reg EQ. I almost always do this no matter what because I've got big fingers and I know I'm going to accidentally click on a different button and all my hard work is going to be erased. Store reg EQ means it's going to store it in the y equals menu. To access the variables, you can either click on the vars button, go to y vars, go to function, and click y1, or there's actually a keyboard shortcut. If you click alpha F4, you can click on y1. Let's calculate, everyone. Bam! It takes just a second because we only did 3 iterations, but here's what we've got. It gives us a different form of our sinusoidal regression. Do you notice what's different about it? Normally, our sinusoidal regression is supposed to be of the following form. It's supposed to be of the form, whoops, that's from a previous lesson. Normally, isn't it supposed to be A, B, sine or cosine, or sorry, A cosine or sine of B times x minus h plus k? Here, the b value is actually in parentheses. Does it matter for us too much? Not really, since we're just building an equation. But if you were asked to find the period of this, then you would actually have to factor out that number to find what the true b value is. We don't care about that for this purpose, though, so we can just go ahead and see what our values are. Since the values are A is 2.764, B is 0.5111, C is negative 1.59, and D is 12.13, C is like our replacement for H, and it's going to be plus C, and D is going to be our replacement for K. Our equation, then, is Y equals, our A value is 2.7647. I'm going to round it to 2.76. It is sine here, even though we kind of saw that cosine would be technically more appropriate. You can transform it if you want. I won't tell anyone. We have our sine. Our b value is 0.51 times x plus our c value. But since our c value is negative, it's actually going to be minus 1.59. And then we have to add our d value of 12.13. Only thing is, I goofed up again, and I didn't look at the units they wanted this in. We wanted this a model that gives n as a function of t. So instead of y and x, we should actually have n and t. But how do we check if we got it right? How do we check if this represents our data truly? Let's go back to the graph. Since we stored it as a regular equation, it's already written right here in y1. We don't need to type anything in. And if we click graph, look at how perfect that is. Is it 100% perfect? No, because it's not a perfect sine wave. But it is the closest approximation we can get. This is our sinusoidal regression, and this is the equation of that sine wave. Everybody, thank you so much for an amazing, amazing year. I hope you have a fantastic rest of your night, and I hope you have a fantastic rest of your summer on top of that. As always, take care.